In this video, we're going to talk about the photoelectric effect, which is another in a series of kind of classic experiments that set up our general belief in the ideas of quantum mechanics. From the first couple of videos, we've seen that those ideas started by being applied to vibrations of atoms and solids, because that was the context both in Planck's explanation of blackbody radiation, and also in Einstein's model for the heat capacity of solids. Those were based on saying that the vibrational frequencies of atoms and solids could be quantized. Today we're going to talk about the quantization of light, right, which is the main result of the photoelectric effect experiment. Its explanation is the beginning of belief in the idea that light can be described as a collection of small increments of energy, what we now call photons. Okay, so let's take a look at the experiment for the photoelectric effect. This experiment, like all the ones we've been talking about, essentially became experimentally manageable somewhere around 1900, give or take. Okay. And so in this experiment, what we've got is we've got a metal surface, and we're going to shine light on it. Okay, so my metal surface is here. I have light coming in, and then I have electrons leaving the surface, being ejected. All right. In order to get this experiment to work properly, we have to do a couple of things. We have to have the entire thing enclosed in a decent level of vacuum, because we don't want those ejected electrons to immediately be able to interact with molecules in the gas phase. So if there's any gas present, that will make it much harder to see the electrons coming off the surface. Okay. That's number one. Number two is we're going to want to ground that metal surface so that it doesn't build up charge over time. If the surface is not grounded, then every time an electron leaves it, carries away a negative charge, that would leave an increasingly positive charge on the metal. If that were the case, then it would get progressively more difficult to extract electrons, and that would definitely have an effect on what we're going to see. So in this experiment, what do we have control over? We have control over what metal we shoot the light at, right? So we could use one metal in one experiment, change to a different metal for another experiment, and we presumably have control over the light, right? So in most cases, we'd say we'd be able to choose the frequency or wavelength of the light, and we'd be able to choose how bright the light is, right? Those would be variables that would be within our control. If we were doing the experiment nowadays, we might say use a tunable laser for the source and just be able to turn knobs literally and adjust those properties. If we were doing the experiment in 1900, we would have had to be a little bit more clever about how to do that, using filters and gratings and things like that. Then on the electrons that are leaving the surface, what can we measure? The first thing we can measure is we can measure how many electrons are leaving the surface, or better say how many electrons per second are leaving the surface. That's a relatively easy thing to measure because electrons help us out with that by having a charge on them. Right? And so since they're charged particles, if we just collect the electrons as they're leaving by letting them strike another metal plate, we can just connect that metal plate into a circuit and measure the current that flows through it. That'll tell us the rate of arrival of electrons at that surface, because we know the charge on an electron, so we can figure out how many electrons it takes to generate that much current. Right? Also, because of the charge on the electron, that makes it relatively easy to measure the kinetic energy of the outgoing electrons. Right? We would do that by taking that plate that's collecting the ejected electrons and gradually turning up a negative voltage on it. There'd come a point when that negative voltage got high enough that it would repel the electrons and they would no longer reach that, that surface, right? Because if I put a negative charge on the plate, negative charge on the electron, there's a repulsive force. If the energy associated with that repulsion gets to be greater than the kinetic energy of the electrons, then the electrons will be turned around. So when I stop seeing the electrons, I'll be able to figure out their kinetic energy from that. So suppose you went back to the 19th century and you asked a physicist, based on what you know about light, what do you think would happen in this experiment? If electrons were ejected, what sorts of things should we see, right? So our 19th century physicist is going to be thinking about light being a wave, because they were pretty sure they understood light that way. In a wave model, the thing that correlates to how much energy is in the wave is the amplitude of the wave, something like, say, the peak-to-peak displacement, right? So if I say, well, I'm going to measure the energy of those outgoing electrons, I might expect that energy to go up if I made the light brighter. Because making the light brighter would correspond to having more and more energy deposited on my metal. It seems like that might result in more energetic electrons leaving, right? So that would probably be the expectation that people would have. If they foresaw that electrons were going to be ejected, that would have been your guess for what was going to happen, okay? So let's look at what actually does happen. This slide includes a set of schematics, or really sort of cartoon versions of 4 graphs that summarize a lot of experimental results, okay? I like to always start by pointing out what's on axes. So let's start with the top graphs. The top graphs have the y-axis labeled as number of electrons. Let's actually think of that as number of electrons per second. I'm feeling like I like that better right now. And then down on the bottom, the y-axis is the kinetic energy. That's the kinetic energy of those outgoing electrons, the electrons that have been ejected from the metal, what we might call photoelectrons. And then let's look at the x-axis. On the left-hand graphs, we have frequency on the x-axis, and on the right-hand graph, we have intensity. Frequency is going to correlate with what color the light is. Intensity is going to correlate with how bright it is. So keep those ideas in mind. Right. Let's start at the top left, because that's the weirdest looking of all these graphs, right? It's got that step function in it, which is definitely a sign that that graph has something to tell us, right? So start at low frequency. If I come down here to the low frequency window, I've got a stretch of frequencies where basically nothing is happening, right? I'm not seeing any electrons, and as the frequency increases, I still don't see any electrons. The experiment is frankly kind of boring because it doesn't have anything actually going on. But then when I get to nu 0, the frequency that's marked down there on the axis as nu sub 0, I have this sudden step up, right? So it's kind of saying this is a yes-no question. If the frequency is below nu 0, nothing happens. If the frequency is above nu 0, then I get electrons being ejected. But other than that, the electrons don't seem to care what the frequency is, right? It's a binary choice kind of result. And again, that should tell us something if we can make sense of it. Each of these graphs, the frequency graphs on the left are assuming the intensity is constant. The intensity graphs on the right are assuming the frequency is constant, by the way. Let's stick with frequency, so we'll drop down to the bottom left. Below nu 0, I can't measure the kinetic energy of the ejected electrons because there aren't any ejected electrons, right? Once I cross through nu 0, that says the kinetic energy increases linearly with frequency, right? So changing the frequency, raising that, is what's actually going to raise that kinetic energy, not the amplitude or the intensity like we had perhaps expected, right? I don't know, let's go around, we'll go counterclockwise. So we'll go to the bottom right over here. That one says, obviously the left-hand graphs have to be taken at frequencies above nu 0, because otherwise there's nothing happening. I can't measure anything, right? This says the kinetic energy is not dependent on the intensity, right? Making the light brighter does not change the energy of the electrons. Again, that's at odds with what I had said I thought our 19th century physicists would expect. It's another surprise result. Up here, the last graph says, as I raise the intensity of the light, I get more and more electrons being ejected from my metal, say each second, right? So the number of electrons depends on the frequency, in as much as the frequency has to be high enough, and the number of electrons definitely depends on the intensity of the light. The kinetic energy depends on the frequency or the wavelength, since those are the same property really, but the kinetic energy does not depend on the intensity, right? So people try, and no one can make sense of this in terms of wave properties of light, right? It's a real stumper for the physics community at that time. And again, this is the same time period where the proposal of quantization is going on in other contexts. And so perhaps as a result of that, it's Einstein who actually first explains this photoelectric effect experiment in terms of quantization and well, quantum mechanics, as we're calling it now, right? And that quantum explanation is based on just a postulate that light can be thought of as being a collection of photons. A photon is a particle or packet or some sort of discrete increment of light, of energy, essentially, right? One of these photons interacts with one electron in Einstein's description of what's going on. Each photon has an energy equal to h nu, right? And that's actually mimicking what Planck proposed in talking about the black body radiation, right? He said that the frequencies, the energies had to be multiples of that h nu quantity. So that's really what's happening here. It says our beam of light really consists of a collection of some number of these photons, and each photon has that relatively small increment of energy of h times nu. Right? It's small because h is a very small number, right? In SI units, h has got 10 to the minus 34th power on it, so it's not a lot of energy that a photon carries. The kinetic energy depends on the frequency, or therefore on the wavelength, right? Remember, the general result for waves is that the speed of the wave, which since we're talking about light, we're going to call c, is equal to, not h nu, is equal to lambda nu the wavelength times the frequency. So if I know wavelength or frequency, I get to know the other one because I always know the speed of light, right? So that's the result, is the kinetic energy depends on the frequency. That makes sense in the sense that if every electron that gets ejected is being ejected by one single photon, the more energy that photon has, then the more energy it might be able to supply to the departing electron. Okay, and that in fact is what successfully explains all those graphs that we had. That threshold energy, the nu zero point in the graph, that corresponds to the energy that's needed to be able to get the electron and tear it free from the metal. Think about it this way: if the metal is sitting there and if I don't turn the light on, the metal is not just going to start spitting out electrons on its own, right? That's not a reasonable thing to expect to happen. The metal is stable. After all, the electrons will not just start flying out of there. Right. So in order to get the electron to leave, we have to first overcome those attractive forces. In terms of physics arguments, we would say there's the work energy theorem, which says some of my energy is used to do work to separate that electron. Right. That says that h nu is the energy of the photons. That's the total energy that's available. Right. Initially, the photon has energy. The photon is coming in and interacts with the metal surface. The photon is absorbed. Essentially, it's destroyed. The photon is not with us anymore. Right. So where does that energy go? Some of it goes to overcome the work function phi, and the rest of it shows up as the kinetic energy. Right. If we take this equation and rearrange it, I could have written h nu is equal to the kinetic energy plus that work function phi. The photoelectric effect is often mentioned somewhat briefly, usually in general chemistry classes. If you have a vague memory of it from there, what we're calling the work function here is often in Gen Chem books referred to as the binding energy of the electron, because that's a little bit more of a chemistry kind of term for it. Okay, I know that's the phrase we use in my 107 textbook, is that it's known as the binding energy. Physicists, solid state physicists generally refer to this as the work function, so we're using the more generally properly regarded term in this case. All right, so let's flip back to the graphs for a second and just see how our photon idea makes sense of all these. Right? If I'm in this first region over here where I have nothing going on, then that just says my photon energy is not as big as the work function. Right? It's not possible to get the electron torn free, so the electron can't leave. It's still attached. Right? If I take at nu zero, my photon energy is just equal to the work function, right? So my electron comes off, and right at nu zero, my kinetic energy hypothetically would be zero down here, right? Because I have enough to remove the electron, but no energy for it to carry with it. Keep raising the frequency, the photon energy keeps going up, and therefore the kinetic energy can begin to rise, right? So the bigger the photon energy, the more energy is left over to be the kinetic energy. What about the intensity variable over here? In this photon picture, the intensity is how many photons am I throwing at the surface per second, right? The kinetic energy doesn't care about that because every electron that leaves is still the result of one photon having interacted with it, right? And so having more photons doesn't get me faster electrons. Having more photons does get me more electrons, because if I have more photons hitting the surface every second, I'll get more electrons leaving every second, right? So all these results make sense if we flip our mindset into thinking about photons, right? This is, this sort of conundrum that light, there are certain properties, things like diffraction, that we can explain really well by thinking about light as a wave. Then there are other properties that we can only explain if we think about light in terms of photons. Right? This is the so-called wave-particle duality. That's a phrase that pops up in textbooks all the time to explain this idea. Basically, it says that light itself is more complicated in either one of those two models, and we manage or get along by using one model or the other to explain things. The photon model in particular is usually going to be handy when we're thinking about light interacting with something that is on a very small scale. The kinds of systems that we think of quantization as being important, that includes atoms and molecules, which is why chemists spend a lot of time thinking about these sorts of things often. So just a quick interlude here. I like to encourage students to think about the properties. We talk about light, frequency, wavelength, intensity, all those things. Think about them in terms of how you would characterize the light if it was light you could see, okay? Frequency or wavelength, that's two ways of specifying what color the light would be. All right, so if I have red light, that in the visible spectrum, that's relatively long wavelengths or low frequencies. Blue light is on the high frequency or short wavelength end of the visible spectrum, right? That's what determines the photon energy. So the color correlates with the energy of a photon, okay? The brightness of the light, that corresponds with, say, the number of photons per second. right? Because I can have a red light, which has small photon energies, and I could still make it be really bright. That just means I have a lot of photons coming out of it every second. Okay. Similarly, I could have a blue light where the photon energy is high, and I could still dial it down so that it was a very dim blue light. Right? It would still have a large photon energy. There just wouldn't be very many of them. Right? If you think about them that way, it gets a little bit easier, in my experience, to keep the thing straight and to not get yourself tripped up into thinking that the brightness of the light is directly correlated with the photon energy, because that's like saying that blue lights are always brighter than red lights. And if I say it that way, you know right away it just doesn't make any sense. All right, this is kind of an energy level diagram just to emphasize some of the relationship that's important in figuring out what's going on here, right? So in the diagram, I've got energy increasing going upwards, just like we generally do when we draw energy level diagrams. Let's label some of the energies that are in here. This one corresponds to the metal just hanging out, minding its own business before my photon comes along. Okay, so that's just an energy that represents the metal with the electrons all attached to it. Call that our starting point. We might call that 0 if we were setting up an energy scale for this problem, because it's as good a place as any, I suppose, right? Up here, I've got this level that corresponds to an electron leaving the metal. So let's label it as metal plus an electron minus. Okay, like I mentioned, we're going to have to ground the metal so that that plus charge doesn't really survive. But at the instant the electron departs, let's imagine we could catch it and see that there. So that's our label for that one, right? Up here, this higher energy, that just represents the fact that now the electron is running away with some kinetic energy. So this length here, that's the kinetic energy of the electron. This one is the work function. That's how much energy it costs to get the electron torn free. If h nu, my photon energy, is this long arrow over here, then just like in the diagram, the sum of these two, phi plus the kinetic energy, has to add up to be the photon energy. That's a rearranged version of this equation. Okay, just makes it really clear looking at the diagram, that's what has to happen. Left-hand panel, over here, my photon energy h nu is now smaller than phi. Right? So the h nu arrow is shorter than the phi arrow. That means I don't make it up to the energy where the electron can separate. So my electron is still attached to the metal. Even if the metal does absorb that photon, all it's going to do is get an electron temporarily excited to a higher level in the metal. Right? So here I'm not seeing any photons in that condition. Okay, so that kind of shows us why this equation works and how it governs what's going on. This is just a second look at one of the graphs that was on the earlier slide. Right, kinetic energy versus frequency. Come back to this because I want to emphasize the argument that says that I labeled it Ke here rather than E sub k, so maybe that's would have been better if I did that, but that's still the same quantity. So the left-hand side of this equation is my y. It's my y-axis, right? Whoa. Hang on. All right, sorry about that. I hit the wrong thing on the iPad, but I think we should be okay now. So I'm going to proceed as if we are. Okay. Come back to this graph. Whoa, I got a strange line drawn in there. I apologize for that. That happened while the screen was changing sizes. I've already struggled a few times to record this one, so I'm going to bear with it, and we'll see. Hopefully it'll turn out okay. My y here, my x-axis is nu. Right? So this piece, h times nu, that's going to be in the role of mx, the slope term of my equation. And this one, minus phi, is going to be plus b. Right? So that's the equation for a straight line. And this is my straight line. What does that tell me? It tells me that the slope of this line is equal to h. So this would be a way that I could measure Planck's constant. In fact, back before Planck's constant became a formally defined quantity, something that is now pegged at an exact value, this is a way people used to be able to measure Planck's constant and get a pretty good result, just to do this photoelectric experiment. It also tells me here that if I were to extrapolate this line down, pretend that goes on a line, then down here, I'd get to minus phi, right, as that y-intercept. Right? So that would tell me I could measure the work function of the metal, and I could also measure Planck's constant if I plotted this graph, because those would correspond to my slope and intercept terms. All right, this marks, I think, our first calculation of the semester. And so before I jump into this, let me just give you a word of advice. In this video format, my suggestion would be when you come to something where I've got a problem posed and I'm about to work it out, I'd suggest you pause and look at the problem and just contemplate whether you think you have a plan for solving it. Okay. In most cases, including this one, I think the slides that I'm posting will actually have cleaned up versions of the equations that I'll be using when I work through the problems. But problems with the equations solved in front of you have a tendency to look a lot easier than they look if you don't have those things in front of you, right? So I definitely encourage you to start off by just taking a second and saying, do I have some plan for how I would do this? Not necessarily working through the whole problem. I'm not perhaps naive enough to think you're all going to do that. But it is a good way to get yourself calibrated. How am I doing on being on top of things and feeling like I would know a general idea of what to do, okay? So what's the problem say? It says for a certain metal, light at 10 to the 15th hertz, that's inverse seconds if you like that description better, produces photoelectrons with a kinetic energy of 2 electron volts. The electron volt is a unit that there's a good chance you might not be familiar with, okay? It's an increment of energy that is designed for describing the energies of, well, things like electrons, right? It's actually the energy associated with an electron being accelerated through a 1 volt potential is why it's called an electron volt, okay? The fact that my electron here has an energy that's 2 suggests it's a good sized quantity for the energy of an electron, right? We'll see in a second when I do the first part, which says convert that into joules. That'll be on the order of 10 to the minus 19th in joules. And so the electron volt makes it a sort of more human-friendly number. Okay, so first step is just going to be a unit conversion into joules. We're just going to look up the unit conversion factor for that and do that. Second part says, what's the longest wavelength of light we'll be able to produce photoelectrons for this metal? That essentially corresponds to locating where that nu zero is in the graph, right? Because nu zero is the smallest frequency, which would correspond to the longest wavelength. And so we'll do that one second. Let's start by doing the energy conversion one, right? So I start with the thing I know, which is 2 electron volts. I want to convert that from electron volts. So I'm going to put 1 electron volt down here. An electron volt, again, you'd probably have to look this up if you're not familiar with these quantities, but 1 electron volt is 1.6 times 10 to the minus 19 joules. Okay, multiply that out, and I'm going to get 3.2 times 10 to the minus 19 joules. And that's really why we use electron volts, because people don't generally like to work in things where quantities are all in things like 10 to the minus 19th power. It's just not easy for your head to get wrapped around that. That said, when you see an energy of 10 to the minus 19th in joules, that should be comforting if we're thinking about things like atoms, electrons, things like that. That's the general ballpark of energy associated with things on that kind of size scale. So that's a thing that makes me feel like I'm doing a problem right if I get to that sort of an answer. All right, let's go to the next part that says we want to find the longest wavelength. Well, I'm going to write here as lambda max. That's our question, okay? How are we going to do this? Our guiding equation was that the photon energy h nu, I'm in wavelength, or I'm thinking about wavelength here, so I'm going to write that as hc over lambda, and that's going to be equal to the kinetic energy plus the work function, okay? So in the description we had there at 10 to the 15th hertz, we know the experiment is working. There are photoelectrons, they have a kinetic energy. We just calculated what it is, right? So suppose I start increasing wavelength from there. If lambda goes up, what's going to happen in this equation? Lambda is on the bottom here, right? So this term is going down as lambda goes up. If the left-hand side of my equation goes down, then something on the right-hand side has to go down. Of the two things over there, the work function phi, that's a property of the metal, right? That just says how hard is it to pull an electron off of this metal? And that's going to depend what metal I'm working with, right? That shouldn't be up to anything I do with the wavelength, right? The wavelength is just some knob on my instrument, something I can control. That shouldn't convince the metal to hold on to the electrons any more or less tightly, right? So if that one's not going down, then the kinetic energy must have to go down. That raises the question, since it says what's the longest wavelength, how far down can the kinetic energy go? The answer should be reasonably intuitive, and it should be that at lambda max, I expect the kinetic energy to go to 0. right? If the photon energy gets any smaller than that, meaning if the wavelength gets any longer than lambda max, then the photon energy is not enough to overcome the work function, then there are no more electrons, right? So to find that boundary, the point where we're at nu zero, we want to find the point where the kinetic energy goes to zero. To do that, we have to first find the work function, find phi, right? So let's do that first. Phi, if I take the equation and rearrange it, I'll say that's equal to h nu. I'm going to work in nu here because that's the quantity I actually know for the incident light. H nu minus the kinetic energy, right? H is 6.626 times 10 to the minus 34th power in SI units, which are joule seconds for that quantity. Nu was 10 to the 15th given as hertz, but let's just call that 1 over seconds. And then I have minus the kinetic energy, which we just converted to joules. So that's 3.2 times 10 to the minus 19 joules. That first part becomes 6.6 times 10 to the minus 19 joules. And so if I put those together, it's easy enough to subtract them. And that says that I get my actual energy is my work function rather is 3.4 times 10 to the minus 19 joules. Okay, so that gives me my work function. At the point where I'm at that lambda max, if the kinetic energy goes to zero, then this says hc over lambda max is now equal to phi, right? So let's use that. If I flip that around, that will say that lambda max is equal to hc over phi, which if I put in the quantities, 6.626 times 10 to the minus 34 again. Again, I will try to do all the problems for the most part in the course in SI units. This is 3 times 10 to the 8th. That's in meters per second. My work function down here is the number we just calculated, 3.42 times 10 to the minus 19 joules. So out of all those things, I should end up in meters. And so when I do that, I'm going to get 5.81 times 10 to the minus 7 in meters, which would give me 581 if I wanted to put it in nanometers. I did the nanometer conversion there just because that's how I think about wavelengths. That's kind of the standard unit for reporting wavelengths in most circumstances for most forms of light. 581 is kind of right near the middle of visible light. Visible spectrum for most people, the part you can see is generally between about 400 and 700 nanometers. So that 581 is kind of in the middle region of that spectrum. And that's a little bit comforting. It sort of makes me feel like I probably have this right. The 10 to the minus 19 joule number corresponds with the energy of visible light photons. And so if you're calculating something like an energy like this work function or anything like that, if you get a number that's wildly off in orders of magnitude from that 10 to the minus 19th number, there's a really good chance you've done something wrong, probably with units. That's obviously the most frequent way you get off by many orders of magnitude. And it gives you a chance, if you're sort of on the lookout, to catch yourself before you get to attach to an answer that has something fairly clearly wrong with it. Okay. All right, that will conclude our quick consideration of the photoelectric effect. Gives us the idea that quantization is a useful notion, not only for vibrational motion in solids, but also for light. Thanks.